Right, let's dive straight into this. Welcome to This Explainer, where we're going on a rather brilliant journey. We're stepping up the ladder of complexity to discover the physics and, honestly, the real-world magic behind something we experience every single second of our waking lives: sound. We'll be moving from the absolute physical foundations of wave mechanics right the way through to the biological synthesis of how we actually hear. So here is our quick roadmap for today. We're going to cover the nature of sound, how sound waves travel, decoding pitch and loudness, echoes, reverberation, and sonar, beyond the audible range, and finally, wrap it all up with the human ear in action. Okay, Section 1, the nature of sound, the foundations. To kick things off, let's look at the classic vacuum bell jar experiment, which perfectly illustrates our very first core concept. Imagine an electric bell inside a glass bell jar. When the bell is ringing, you can hear it loud and clear, right? But as a vacuum pump sucks the air out of the jar, the sound gets fainter and fainter until it almost entirely disappears. And the crazy thing is, the hammer is still striking the bell. This proves unequivocally that sound is a mechanical wave. It strictly requires a material medium, like a solid, liquid, or gas, to propagate. It absolutely cannot travel through a vacuum. Now, this busts one of the biggest misconceptions in physics. When sound travels from a speaker to your ear, the air particles themselves are not actually traveling across the room. The wave disturbance transfers the energy outwards, sure, but the actual particles of the medium, they only oscillate locally about their mean position, or their center. They literally just bump into their neighbors and return to rest. It's an energy relay race, not a marathon for the particles. Moving on to Section 2, how sound waves travel, compressions and rarefactions. Let's look a bit closer at how this disturbance actually moves. Sound in air is what we call a longitudinal wave. Notice how the particles vibrate back and forth, parallel to the direction the wave is traveling. This creates alternating regions. You get compressions, which are regions of higher pressure and density, where particles are all squished together. And then you get rarefactions, which are regions of lower pressure and density, where they're spread apart. But here is something to really think about. If sound is ultimately just mechanical pressure variations, literally just air getting squeezed and stretched, how on earth do we perceive such a rich, vast variety of musical notes, subtle whispers, and booming volumes? Let's find out in Section 3, decoding pitch and loudness, analyzing the wave. We can easily represent these density variations on a graph. The distance between two consecutive compressions is your wavelength. So first, let's consider frequency. This is measured in hertz, and it's simply the number of oscillations per second. A higher frequency creates a shorter wavelength, and our brains perceive this as a higher pitch. On the flip side, we have amplitude, which is the maximum variation in density. A larger amplitude, meaning a taller wave on the graph, means more energy is transferred, and that is what dictates the loudness. So keeping it simple, frequency is pitch and amplitude is loudness. But wait, there is a third characteristic: timbre, or the quality of sound. If a flute and a piano play the exact same pitch at the exact same loudness, they still sound entirely different, don't they? This concept is deeply understood in Indian knowledge systems. Traditional Indian musical instruments perfectly map to vibrating source categories: strings for the sitar, air columns for the bansuri, and membranes for the tabla. The tabla and mridangam are especially fascinating because of their black central patch. That patch masterfully manipulates the overtones and frequencies of the vibrating membrane, creating a highly complex, unique timbre that you can recognize instantly. Right, let's look at Section 4, echoes, reverberations, and sonar, real-world physics. Because sound is a wave, it bounces off surfaces, but the result really depends on the environment. We have to evaluate the difference between an echo and reverberation. You see, our brains need about a 0.1 second delay to distinguish two separate sounds. If the reflection arrives after that delay, boom, you hear a distinct, separate echo. But if it arrives faster, the sounds blur together into an overlapping persistence. That's reverberation. A stunning architectural example of this is the Whispering Gallery at the Gol Gumbaz in Karnataka. Its massive, hard dome creates repeated reflections that allow even a faint whisper to persist and travel across the entire vast space. So the absolutely crucial point here is how we calculate that distinct echo. To get that 0.1 second delay, the sound has to travel to the wall and then come back. It's a round trip. Therefore, the formula we use to calculate the distance to the reflecting surface is d equals vt over 2. Distance equals velocity times time divided by 2. And listen, the number one mistake students make on exams is forgetting to divide by 2. Always, always remember, the sound is making a two-way journey. Next up, Section 5, Beyond the Audible Range, Extremes of Sound. Human hearing is quite strictly bound between roughly 20 hertz and 20 kilohertz. Anything below 20 hertz is infrasonic. These are massive, slow, rumbling waves, like those generated by earthquakes. On the other end, anything above 20 kilohertz is ultrasonic. These high-frequency waves are incredibly useful for things like medical imaging and industrial flaw detection, mostly because their short wavelengths allow them to reflect off very, very small objects. And this brilliantly illustrates the cross-disciplinary nature of physics. Whether it's a bat navigating a pitch-black cave using biological echolocation or a naval submarine mapping the ocean floor using sonar, they are relying on the exact same principles. They emit ultrasonic pulses and calculate the distance to the target based on the time it takes for the echo to return. And yes, they're essentially using our trusty round-trip formula, D equals VT over 2. Finally, Section 6, the human ear in action. Biological synthesis. All these physical properties we've discussed, compressions, rarefactions, frequencies, amplitudes, they actually mean absolutely nothing to us without a biological receiver. The human ear is an astonishing piece of natural engineering. It's designed specifically to transform those mechanical pressure variations in the air into the subjective, beautiful experience we know as sound. Let's trace that anatomical journey. First, the outer ear, called the pinna, collects the sound waves and funnels them down the auditory canal. These waves strike the eardrum, causing it to vibrate. These mechanical vibrations are then passed to the ossicles, which are 3 tiny little bones in the middle ear, and they amplify the motion. But the true magic happens in the inner ear, inside a coiled, fluid-filled structure called the cochlea. Here, sensory hair cells take those mechanical vibrations and convert them into electrical nerve impulses. The auditory nerve then rushes these electrical signals to the brain, which finally interprets them as sound. It's just a stunning conversion from mechanical energy straight into electrical energy. And there you have it. We've gone from a vibrating tuning fork all the way to the electrical impulses firing in your brain. But understanding the theory is just the first step. To truly excel, you need to move from passive watching to active mastery. And for that, I highly recommend visiting edunudge.in today. On edunudge.in, you'll find comprehensive CBSE-aligned question banks that test these exact concepts. They feature higher-order thinking skills, or HOTS, with competency-based scenarios that actually force you to apply what you've learned. Plus, if those wave speed and sonar maths calculations with our round-trip formula are tripping you up, their unique 5-step nudge system is going to help you conquer them with total confidence. So as you go about your day, listening to the world around you, ask yourself a rather strange question. Does sound actually exist out there in the world? Or is the universe perfectly silent, waiting for your brain to paint it with the illusion of noise? Thanks for exploring with us, and keep questioning.